Hello, my name is Sam Billand, and today we're going to be talking about Lab 2, Lines of Charge, from Physics 2212. First, the purpose of this lab is to determine and calculate the deficit of charge on a piece of positively charged U-tape, and this is done by analyzing the effect of the electric force from a similarly charged piece of U-tape. Then, a computational model is created that better represents the electric field using lines of charge and separated point charges. Before the experiment could be performed, initial observations were made about charged tapes and their interactions. When brought together, two pieces of charged tape repelled each other. Charged tape attract to neutral objects through polarization, and the charged tape attract to negatively charged plastic pens. Therefore, through these three conclusions, you can assume that the U-tape is positively charged in the experiment. Next, here are some of the main physics principles applied and assumptions. First, there is the electric field of a point charge equation and the electric force of a point charge equation, both of which are vital to the calculations in the coding. Next, there are two main assumptions in this lab. First, the sections of tape are considered to be point charges in calculations. Now, this does not mean the whole tape is considered to be one point charge, but each little section of tape is considered to be its own point charge with corresponding charge and mass. Next, both U-tapes are given the same amount of positive charge when being charged. While the processes performed in this lab are very similar to Lab 1, there are still some main differences. First, the computational model in Lab 2 is meant to give a better representation of the electric field and electric force from charged U-tape. The charge is spread evenly across the length of tape as n number of point charges with equal share of mass and charge, and this is meant to create a more accurate result and a closer estimate to the actual charge on the U-tape. When creating the computational model for Lab 2, I first started with inserting the constants and observed values from the experiment. This included charge and mass of tape. Then, I inserted the electric field function created from Lab 0. Then, I created the line charges using the function above, and inserted two lines with a separation distance of 0.02 meters with 15 point charge nodes. Following this, I set the scale of the electric field and gravitational force arrows for proper viewing. Finally, I iterated through each tape to create the electric field at each point charge on the top tape by the bottom tape. Following this, I calculated the electric force at each of the point charge nodes. Below this is an arrow representing the summation of the electric forces on the top tape, and the gravitational force arrow, which is followed by a print statement of these values. When the code is run, it looks as it does on the right. This is correct because the tape is shown having multiple point charges, and the electric field lines on each point charge sum to an upward-facing electric force. And finally, the net force on the tape is relatively zero, and the total charge on the tape comes to be 1.3 times 10 to the negative 8th coulombs. When looking at the principles to model connection, the main connection is that the forces are in equilibrium on each charged tape. Overall, the electric field on the tape is calculated through the line charge electric field equation shown below, and this is a summation of the individual point charge electric fields, represented by the green arrows in the computational model. In using these values, you can easily solve for Q, which is the charge on the tape, given by the line charge electric field equation. When asked what would happen if you modeled each of your tapes as a single point charge, like in the previous lab, you will come to see that Lab 2, using the line charge model, generates a more accurate value for the charge on the tape than Lab 1 and its point charge model, both of which are shown below. So, why do these estimates differ? Which value is more likely to be closer to the real value, and why? First, the charge calculated in this lab using the line charge model is closer to the real value of charge. They differ because line charges break total charge into small, similarly charged pieces across the whole tape, allowing for a better distribution of the electric field. And then the summation of these electric field pieces create the overall upward-facing electric field that is more accurate than the singular point charge model. In conclusion, the final magnitude of charge left on one piece of tape when considering the tape to be a line charge is 1.3 times 10 to the negative 8th coulombs. So through experimentation and calculations, it is easy to determine the deficit of charge on any common everyday object. And this is done by breaking down charge into many point charge pieces, and it creates a more accurate electric field representation.